Axisymmetric problems occur in mechanics quite often. Many people think of axisymmetric problems as lathe pieces. In other words, pieces turned on a lathe about an axis. Another word often used is a body of revolution. There are many people who spend their whole lives studying bodies such as this, particularly if you work with shafts, rotors, things that are rotating bodies. I think for this reason some of the commercial codes work pretty hard on axisymmetry. I've heard, for instance, that ANSYS has a lot of load capability in that area. Other codes might use axisymmetry in a cyclic symmetry sense, and that's the way MSc Nastran does it. So you'll find axisymmetry embedded in the different commercial codes in different ways. Some of the codes will allow that axisymmetric element to be a full ring in 3 dimensions, and other codes will restrict that axisymmetric body to be merely a slice in the XZ plane, say. But overall, there's some worry about trying to assemble axisymmetric ring-like elements with other elements, and in general that's not done. One reason is that the loading and many of the properties of the axisymmetric element are essentially smeared out around the circle, and so the match between that and conventional elements can be rather brutal. So in general it's to be avoided. Now, I'll do a little overview showing some of the geometrical ideas and the stress and strain concepts. We'll look at a 3-noded triangular element that's somewhat of a generalization of the Turner triangle in plane stress. We'll look at 4-noded quadrilaterals and talk a minute about 6-noded triangular elements. Then an application will be the Lemay problem, where I will take a ring under internal pressure and then show solutions using 2 computer codes and discuss the results. Finally, we'll end up with a problem session. Many people call the axisymmetric element a ring element for obvious reasons. Here's a sketch of a ring element shown in an oblique view, and it is a 2-dimensional element in the sense that if you draw a particular plane that passes through the axis of symmetry, you'll get a 2-dimensional shape as shown here, cross-hatched in black. Then the loading generally would be applied on that plane. Now, some computer codes, though, will allow harmonic variation in the azimuthal direction, and so you have to decide whether you're going to have axisymmetric loading as well as an axisymmetric body or not. In the cyclic symmetry terminology, this is called harmonic zero loading. The interesting thing then is whether or not, as a 2-dimensional slice here, and when you have axisymmetric loading also, or harmonic zero loading, does this body act more like perhaps plane stress or like plane strain? And it turns out that at a specific local point it looks more like plane strain. Well, let's follow this through. If we consider only axisymmetric loads, and I think that's what I'll concentrate on in this lecture as an introductory topic, then the V direction displacement is in the azimuthal or theta direction, and it is 0. So the body doesn't tend to spin about its own axis. Then the U displacement in the vector sense with both U and W components would lie in the RZ plane. Sometimes it's characterized as the XZ plane, as in the Nastran codes. So we're going to try basically to eliminate the effects of this azimuthal displacement field and try to concentrate on solving the problem in the RZ plane. It's possible in both stresses and strains to concentrate on 4 components. Now, it's not that the other 2 components are all 0 in both stress and strain, but rather that they can be easily determined in terms of these 4. We have the radial and the Z strains. Then we have the theta direction, the azimuthal or hoop strain. And then you have the shearing strain in the plane. Now the two shearing strains out of the plane, if you have axisymmetric loading, are both 0. Now for stresses, you'll want to keep track of the radial stress and the Z stress. The hoop stress is always a factor if you're thinking of fatigue or failure theories for the material. And then you have the shear in the plane. We've discussed stresses and strains in basically 4 directions, you might say. And the one that actually you might have the most intuition about is the hoop direction. If I take a rubber band and put it on my fingers and then treat it like a ring element and then try to expand it, the one force that I really feel is that force tending to bring that ring back down again to its unstressed position. So we all should really have some intuition about the hoop strains and the hoop stresses. Forces are a little more ambiguous in the sense that a computer code might ask you for loads per running distance around the ring direction. They could be a per surface area, they could be per volume, it could be most anything. But it turns out that some of the code, such as the Nastran series, define forces pretty much as a total force around the ring. So be careful when you use your own commercial code as to exactly how that's defined. And then secondly, you want to know whether your application, first of all, and then whether the code you use is able to handle non-constant loads around the ring. And if so, if you do have non-constant forces, then you either need to use a Fourier type analysis that's allowed in some of the programs, or go into cyclic symmetry in the Nastran series. Now, the variables that we're going to discuss fall into that same pattern as the flowchart that we've shown before, that we'll have nodal displacement quantities and nodal force quantities, and then we'll have the mapping interior with the classical field variables, the 4 variables here on stress, 4 on strain, 2 field displacements. And then remember that you'd like to balance, if there are generalized coordinates here, the number of generalized coordinates to match the number of nodal coordinates so that you can appropriately map back and forth. Then when you use that method, you have a mapping matrix H that can be inverted. Sometimes people would rather map, of course, directly from nodal displacements to the field displacements. If we look at the mappings that are involved in that flowchart, one of the first ones is the material law, sometimes called the constitutive law or stress-strain law. This matrix G relates the strains to the stresses. And it will turn out that when you go down to a point, and this is a law at a point, that this is the same as plane strain. You may want to stop and look at this and look at some reference books on this topic. It means that successive slices from this ring-like body, as you pass around in the azimuthal direction, are being constrained by the neighbors in a way that they can neither slide right nor left. And that's very similar to plane strain if you think about it. So locally, a point doesn't feel the curvature as much in this material law as it does feel the fact that it's trapped to move in the plane if the loading is axisymmetric. And therefore you end up with something that's the same as a plane strain relation. The strain displacement law is a little more global in nature than the stress strain law, and that is because there are derivatives involved, it feels around the neighborhood a little more, and it is influenced by the radial distance. The general law is that strain is d times the displacement field. Our displacement field consists of the u and the w displacements in the RZ plane. You'll see here that the epsilon x and the epsilon z play the same role as a conventional two-dimensional problem would, and likewise the shear, but that the hoop strain varies as the displacement u, if I bring this down here, let me repeat this from up above, and then you see that this multiplies the u component, and so that the hoop strain depends only on the radial component of displacement divided by the local radius. So the radius does affect the strain law. And I point that out here below in scalar form. Let's look at some candidate ring-like elements in axisymmetry. And the first one that you might think of would be a three-noded triangle. This would be an attempt to generalize something like a Turner triangle into the axisymmetric region. Then there's the question, is that a constant strain triangle or not? Well, the three-noded triangle would have these 6 degrees of freedom shown, and you could write out the displacement function rather obviously then as a set of linear polynomials both in the u and the w displacement fields. We can write out the strain displacement law in a matrix form, and here we define the phi matrix and show the 6 generalized coordinates on the right here. Now, in order to get a mapping from nodal coordinates to the field variables, we need to do the trick of evaluating the interior field variables at the nodes and then develop this H matrix. So that's done by evaluating these phi functions at the nodes in turn, as shown here, and results in this matrix. We now have all the mappings that we need for our three-noded triangular axisymmetric element. Here's the general formula for any elastic body, and then below we show the detailed formula. The classical values are in the interior, where we have the strain displacement law, then the material law, and then the strain displacement law again. We've assumed the displacement functions in polynomial form. We know how to evaluate H by evaluating those displacement functions at the nodes, and then we know how to invert. It's better if you factor out the constant H matrix to the rear and to the front of the integral so that it doesn't complicate the integration. So in principle, we could analytically integrate that, but in practice, numerical integration is used more often on such finite element problems. The equivalent nodal loads are likewise found. They depend on the shape function, which can be broken into the pieces of the H matrix inverted and the displacement function. Well, that concludes our study of the three-noded triangle, and if you've thought about it by now, you'll realize that the hoop strain is not constant in that element, so it really isn't a constant strain element in the three-dimensional sense. Now let's move to the more general case of a quadrilateral. We can use an isoperimetric concept, mapping a quadrilateral to a double unit square. Then we can evaluate on that double unit square, which we call the parent element, by defining shape functions there, and it's rather easy to do that on the parent element. I'll sketch the original physical element and then how it's mapped into the parent element. Here we have our four-noded quadrilateral, and here's our parent element. And the shape functions that are defined on the parent element are shown here. These have that repetitive nature due to the reflective planes of symmetry of this parent element. The shape functions are used to map both the independent and the dependent variables. Here we show the independent variable mapping, and that helps define the new element domain. And then here are the dependent variables that help define how the variables are acting in that domain. Now we can come up with the stiffness formula here, and we know the classical quantities again for geometry and material, and we have come up this time directly with shape functions that are the remaining need. The integration of the stiffness matrix is handled in two ways. First, in the theta direction, you proceed with an analytical integration, but then in the C-eta plane, you carry out a numerical integration. So we'll presume that the theta integration has been done, bringing out a 2 pi. Now we're worried about the C-eta integration. And I've shown here the general form then after transformation to those isoperimetric variables, so that we have the determinant of the Jacobian entering. So this is quite normal and standard practice now. Likewise, with the equivalent nodal loads, we know what the shape functions are, so we can handle those. If we're in our C-eta theta coordinate system, then we can again, on the equivalent nodal load, integrate analytically on the theta dimension and be left with the integral on the C-eta. So in either case, you end up with a numerical integration in a plane. Many people feel that the 6-noded triangle is the best of the axisymmetric elements. Other people allow solid elements to be used in an axisymmetric way as per the cyclic symmetry in MSC Nastran. So I think the user has to decide which way to go. I have done both the conventional axisymmetric elements and the cyclic symmetry, and they both have advantages. If you're in a code where the axisymmetric element can be extended into the non-axisymmetric loading, that is, higher harmonics of loading, then this would be quite useful. If you're in codes where you don't have that capability for axisymmetric harmonic loading, then you might better use the solid element and go into cyclic symmetry, such as the Nastran codes. A very famous axisymmetric problem is called the Lemay problem, or the gun barrel problem. Here you have a thick-walled cylinder that's being pressurized both on the inside and the outside. The solution can be extended either to the plane strain case or the plane stress case. But it's particularly nice in that for internal and external pressures you can get closed form solutions. If the loading is axisymmetric as shown, and that means harmonic zero loading, then really the problem's one-dimensional because the only variation is with stress through the thickness and displacement through the thickness, and there are no changes in the theta direction. The solutions to the Lemay problem are well known and are easily found for both internal and external loads acting. But let's just write down the solution for the internal load case. You get this pair of stresses for radial and the hoop stress. I don't have external forces acting. An interesting thing is that if you add these up on both sides, you'll see that you get cancellation of these terms and that the sum of the two is constant. Now, because of that, it turns out that the Lemay solution can be used for plane strain as well as for plane stress for long and short bodies, because there's no tendency for the cross-section of a plane normal to the rotational axis to go out of plane. The body tends to expand and contract uniformly over the face of that cut normal to the axis. From what I've just said, it seems reasonable that you'd get the same results in a short washer, which could be plane stress, as well as a long cylinder free to expand. That would be kind of a generalized plane strain, because the body would tend to expand uniformly. A further claim is made, though, and it is that the plane stress solution for the ring also gives correct stresses for a cylinder with restrained ends. Now this is a little bit harder to see. This is a plane strain problem. Now you wouldn't have the same displacements per se, at least in the axial direction, because this would be confined. Now I've mentioned that the Lemay problem is really a one-dimensional problem, with the radial coordinate as the important one. We can also view this as an axisymmetric problem, though, and we'll take a small washer as an example of this, an internally pressurized washer. It's 50 millimeters across, it's 110 millimeters in the outside diameter, and 50 millimeters in the inside diameter. The internal pressurization is 100 megapascals. The cross-section that we will consider here to be our axisymmetric cross-section is shown cross-etched in green, and the axis of symmetry is shown here as a straight line. This means that the two-dimensional problem that we're looking at with the RZ coordinates pointed out below are such that there shouldn't be much happening in the Z direction, and all the action happens in the R direction. We'll assume that this little body is free to expand then on these two faces, and there are no loads there, and hence this will be a plane stress problem in addition to being an axisymmetric problem. I'd like to do a small demonstration problem finding the stresses in that axisymmetric washer that we just described. And I'll use two commercial codes. I'll actually use MSc Nastran to lay out the problem, and then we'll also run the problem in Mark and compare the stresses that are obtained. The mesh will be rather coarse, so the answers won't be real precise, but they'll be pretty good. In the MSc Nastran code, the Triax 6 is the recommended axisymmetric element. It's developed in the RZ plane, but in fact you use the basic coordinate system with XZ coordinates to describe the grids. We'll assume that the loading is axisymmetric so that there's no azimuthal displacement throughout the ring, and this particular element uses a 7-point integration scheme, so you can see that it's an isoparametric element. Let me show you the sketch of the mesh that we'll use in our two solutions. Here are six noded finite elements. The inner radius of our washer is on the left with the 100 megapascal loading shown. The rotational axis is shown as the z-axis. It's at a distorted distance from the inner radius. It's really farther away. Then the free outside surface is on the right. Now there's one rigid body mode that could occur for this kind of an axisymmetric problem, and that would be translation in the z direction. And that's why I have constrained the one centrally located node, number 8, in the W displacement direction. And that will remove the rigid body mode. I'll show the MSc Nastran data. Here you have the executive deck, and this was a file management statement ahead of it. We'll just call it Lemay prob, and allow as much as 5 minutes on our Hewlett-Packard. We'll use Sol 101, the more modern static solver. In the case control, we ask to echo out both the raw and the sorted data. The control data deck continues. Here we have the request for output of all kinds of displacements, stresses, element forces, and to output the loads, because the distributed pressures we would like to check and see if they really are what we think. Now remember, on many codes, this is the entire load all around the body, and that's true in Nastran, for instance. So this will look like a ring load, it will turn out, and will be a concentrated ring load at a given node. We ask for the SPC forces. The only one that we have is that one constrained degree of freedom, and it ought to be 0. So this is really just a check. There's just one load case, case 50. Now, the plotting that I'm calling for here, I regard as a bare bones built-in plotter that nowadays people tend to use Patran and Excel, Mentat, Ideas. There's a number of commercial pre- and post-processors. I'll leave these cards in, though, just to show the viewer what a built-in plot package might look like. The bulk data deck is shown next. I do have the call for Patran output for graphical purposes. I'm using a grid set card that's restraining 4 of the 6 degrees of freedom as the default over the whole body. This will convert our problem definitely into a axisymmetric situation where we don't allow any y displacements. That's the number 2. And there are no rotations defined for the axisymmetric element. It's an elasticity element in that sense, as opposed to a structural element that has moments and rotations defined. On looking at the grids, I've set up what is called a step and repeat feature in MSC Nastran, where the equal sign means that you can repeat the card preceding, and a double equal means you continue all the following fields. Then you can increment with the star and a quantity in the parenthesis so that we can increment the ID number of the element, for instance. Then this equals, and then 5 in parentheses means to do the same thing 5 more times. And so I've actually laid out the grids and the elements by using this approach with the so-called step and repeat feature. We'll conclude the input data on this figure. One more set of elements to be connected. The material card here is for steel with Young's modulus and Poisson's ratio. And then there's a special load card, P load X, for axisymmetric cases. You can vary the load along that loaded face if you wish. Ours will be a constant 100 megapascals of load over the pressurized face. And then that's the end of the data. A diagnostic that's put out early in the Nastran run is the value of epsilon. This is a measure of how many significant figures remain, because it's a ratio of the force on balance at a node compared to the forces at the node, and so it gives you some measure of how much precision you're losing, or round off errors, in other words. Now this is an extremely small number here, and due to the fact that we have so few equations that we're solving. Another interesting item that's printed out is the external work that's done. That gives you some idea if the system is allowing the loads to move through inordinately large displacements and creating a lot of apparent energy. That could happen if you had a mechanism in the problem, for instance. This number shown here in Newton millimeters is not unreasonable for such a stiff body, and it's really not an awful lot of energy. More diagnostics involve the output load resultants and the single point constraint forces. The single point constraint force at that 1 degree of freedom that we had constrained to remove rigid body mode turns out to have only 2 times 10 to the minus 9 newtons. And you can see that's a very small amount, so effectively there's no load being carried by that constraint. The output load resultant shows the resultant thrust outward on that face, and it turns out to equal the entire pressure load on the entire radius of the ring. And so that indeed is a ring load. I'll summarize some of the output on this next figure. Here we have the actual equivalent nodal loads at the 3 loaded nodes at the inner diameter. Here's the force on the restrained degree of freedom. Here's the radial displacement at the inner diameter and then at the outer diameter. Notice that the inner diameter is moving outward more than the outer diameter, so in effect the outer body is holding back the inner radius. I'll briefly show some of the tabular results for stress from the MSc Nastran run. Actually, the more interesting way to see this will be graphical, and I'll follow with those figures that plot the numerical answers versus the Lemay solution. The first element in our solution has a node number 1 on the inner bore, and it gets 82 megapascals in compression and 158 in tension. Now, this number here should be compared with the load, which is 100 megapascals, and so we're not matching in this element, which actually lies inboard a bit dominantly, but we don't match up with the surface pressure. Likewise, the fourth element has nodes on the inner boundary. It has both nodes 15 and node 1, and these numbers then are also approximations to the 100 megapascal compressive loading on that boundary. This isn't bad. It's only a matter of the approximation that we're making. Those elements are trying to come into equilibrium with those concentrated equivalent nodal loads, and to the best of their ability, this is the stress that they would predict at that boundary, having been loaded with those concentrated forces. The next figure is a little busy because I've combined some results from MSc Nastran and from Mark. Again, the pressurized boundary, the inner bore, is on the left, and the outer unstressed boundary is on the right. The triax 6 element gives stresses at the external nodes here, the vertices, but not at the mid-sides. But the Mark element, their number 126 element, does give stresses at all 6 points. So I've included those just for the fun of it. So these stresses definitely are attempting to reach the 100 megapascal level at the inner boundary, and they're trying to reach 0 stress on the outer boundary for radial stress sigma r. Now let's compare both of the finite element solutions to the classical Lemay solution. First, we'll talk about the radial stress, and the Lemay solution is in red. Of course, it's only defined over the domain of the problem, which runs from 50 millimeters out to 110 millimeters. And notice that even with this rather coarse mesh, we're getting answers that are within 10% roughly. Well, let's say 13%, I should say. And the stresses fall a bit short at the inner radius of meeting the applied pressure there. And then they bounce around a little bit on the interior of the body, and both attempt to reach 0 at the outer radius. Finally, we'll look at the azimuthal, or the hoop stress in the washer. And here we see that the two finite element codes are within 9% of the exact answer over the range of the solution. So that looks pretty good. And this is a little higher stress level. In fact, this hoop stress probably would contribute more toward the failure of the body, since it's in tension and might be more effective in cracking the body. Now, I've done a couple of axisymmetric consulting jobs in my life, and they were both interesting. I would certainly encourage people to try axisymmetry. It doesn't come up as often as sheet metal work and solid work in general, but the codes are very effective. Before we start our problem session, I'll tell another story. A few years ago, another professor came to me with an axisymmetric problem and asked if I would help him. He was working on a hot project and needed some finite element work. And it was a set of ring-like bodies that were overlapping each other, pressing on each other, shrunk fit against each other. And I looked at it, and when I saw the material properties, my hat popped off, and it turns out the stiffnesses of the material, of the various materials, were really high, 70 and 80 million psi, which is some 2 or 3 times that of steel. And I said, "What are you making this out of? This must be tungsten carbide, and you must be making diamonds." And the professor, oh no, he said, "You're not supposed to know that." And it turns out that's what it was. It was a diamond making machine. And of all the projects that I've worked on that I would have loved to give in as case studies, that has to top the list, and I can't talk about it, unfortunately. I promised I would never tell any details about that. But it was fun anyway, and it shows the frustrations of a professor when you get to do interesting things and then you can't blab about them. Okay, let's go into problem number 1, 4-noded quadrilateral. I'm going to propose a problem that's a little bit mathematical in a sense. I sort of wanted to work the viewer through some of the stress and strain concepts. I have here a quadrilateral ring element, 4-noded, and we're going to impose a displacement field. We're going to put a uniform radial displacement of 0.001 millimeters, and then we're going to presume that the body contracts towards its center line in the plane perpendicular to Z by 0.003